Welcome to Shanti-Peace for Mathematics. In the previous video, we have talked about the equality of mixed partial. It says that f of xy at point AB is not equal to f of yx at AB. In general, this is not equal. These two quantities are not equal. That we have seen by an example. Also, we have seen the squash theorem for that, and we have seen the proof for that in the previous video. Today we will discuss about the Young's theorem. So Young's was a mathematician. Due to his name, this Young's theorem is well known. It also talks about when the f of xy is equal to f of yx. So let us state the theorem. What is that theorem says? Let f d belongs to r square to r be a function and x0 y0 belongs to d. So there is a function is there, and also there is a point which is belongs to b. Consider the neighborhood of this x0 y0. N as n is a neighborhood of x0 y0. Now two conditions should satisfy. The first one is fx and fy exist in n, and second one, fx and fy are differentiable at x0 y0. Then prove that fxy and fyx are exist at x0 y0 and fxy at x0 y0 is same as fyx at x0 y0, and this is known as Young's theorem, and it is very well known theorem for equality of mixed partial. So let us try to discuss the proof of this theorem. So in the squash theorem, what is happening? In the squash theorem, you will have this the continuity of the one of the mixed partial is given. If fx is exist, then fyx is continuous. That are the condition. Here the differentiability of fx and fy's are there. So that is the change in the squash theorem and Young's theorem is there. If you want to check whether the partials, mixed partials are equal, then you have to either you can use the squash theorem or Young's theorem, whatever you like. Proof for this, given that n be a neighborhood of x0 y0. So I am taking this neighborhood, this point x0 plus h, y0 plus k is belongs to n, and which is a subset of d. Now due to this I am defining a one function. So define a function phi of hk is x0 plus h y0 plus k minus f of x0 plus h y0 minus f of x0 y0 plus k minus f of x0 y0. The same function we have defined for squash theorem is also, it is the same things we have here. Now again another things I am defining as a function of one variable, that is a g of x, as f of x y0 plus k minus f of x y0. If you can observe this phi of hk, this two quantity, if you want to write down in terms of g of x, then instead of x you will have here x0 plus h. So this two quantity is nothing but the g of x0 plus h, and here we have a plus sign. So if you have here plus, then these two quantities, that is minus of this and minus, so here x0 is there, so that's why this is nothing but the g of x0. So what we can say is phi of hk we can write as g of x0 plus h and g of x0. So this is the way you can have this. So let us call this 3 equation as a number. So I am giving you this is as a first number, this one as a second number, and this one as a third number. I am denoting by as equation 1, 2 and 3, these 3 equations. Given that fx and fy are differentiable function at x0, y0. So since they are differentiable, its partial derivatives are exist. So we can say that therefore fxx, fxy, fyx, fyy are exist at point x0, y0. Therefore what we can say is, since these are exist, I can say that fx is differentiable at x0, y0. So as per this equation number 2, that one is this, we say that since fx is differentiable, this g is also differentiable with respect to x, because g is only one variable function. Since fx is exist and it is differentiable, we can say that this g is also differentiable. So that or we can say that g is differentiable in the interval. Which interval? The interval of x. What is that interval of x? Is x0 to x0 plus h. So in this interval, this g is differentiable. Also it is continuous. So we can apply the Lagrange mean value theorem, and we will recall what is Lagrange mean value theorem. It's known as LMVT. So it says that if f is a function from x0 to x0 plus h to r, which is continuous on closed interval x0 to x0 plus h. Second one, f is differentiable in the open interval x0 to x0 plus h. Then there exists a theta belongs to 0, 1 such that f of x0 plus h minus f of x0 upon h is equal to f dash of x0 plus theta h. Now due to this, here we have g is continuous in the closed interval x0 to x0 plus h, g is differentiable in that interval. So therefore by LMVT, that is Lagrange mean value theorem, there exists a theta in belongs to 0, 1 such that g of x0 plus h minus g of x0 upon h is equal to g dash of x0 plus theta h. Now what is this g dash of x0 plus theta h? Due to equation 2, what will be the derivative of this quantity with respect to x? The derivative of this quantity is, from equation 2 we can write g of x is f of x comma y0 plus k minus f of x comma y0. So if I differentiate this with respect to x, we'll have f dash of x, which is fx at x comma y0 plus k, fx at x comma y0. If I call it, this is as equation number 4 and this is as 5. I may use on this side this value f dash of x, that is x0 plus, instead of x I may replace x0 plus theta h here. On this side, the numerator that we have from equation 1, what is the equation 1 we have here? That is this phi of hk. It is this, and so in equation 3 we have written phi of hk is this. So if I use the equation this 5 and 3 in 4, so using equation 3 and 5 in 4, we get, so here we have phi of hk upon h. On this side we'll have fx at x0 plus theta h, comma y0 plus k minus fx at x0 plus theta h, comma y0. So hence you will have this is as phi of hk equal to h into fx at x0 plus theta h, comma y0 plus k minus fx at x0 plus theta h, comma y0, and I will call this as equation number 6. Now what is another thing is given, also given that fx is differentiable at x0 y0. You just recall the definition of differentiable function. As per the definition we can say that there exists some function a and b such that fx at x0 plus h, y0 plus k, fx at x0 y0 plus h into a plus k into b plus h into epsilon 1 hk plus k into epsilon 2 hk, where epsilon 1 and epsilon 2 tends to 0 as hk tends to 0. They are the functions of h and k, and they are tends to 0 as h and k tends to 0. This is the definition of differentiable function. I am just replacing here instead of h by theta h, and instead of a, what is a is actually a partial derivative of this function, whatever the function is there with respect to x. So what is the a value of a is, that is fxx at x0 y0, and the value of b is nothing but the fxy at x0 y0, because actually that is the things we have. So therefore we can get is fx x0 plus theta h, y0 plus k equal to fx x0 y0 plus h. Instead of h we have to write down theta h, so that's why it is theta h fxx at x0 y0 plus k fxy at x0 y0 theta h into epsilon 1 theta h into k plus k into epsilon 2 theta h into k, where this epsilon 1 and epsilon 2 tends to 0 as hk tends to 0, because see, if the h tends to 0, theta h is also tends to 0, so there is no problem with this condition. Now if I put k equal to 0 in this, so putting k equal to 0, we get fx at x0 plus theta h, comma y0, because k is 0. This is fx at x0 y0 plus theta h into fxx at x0 y0. K is 0, so that's why this term is 0, plus theta h epsilon 1 theta h comma 0, because k is 0 and this k is 0, so that's why it is tends to 0, and this epsilon 1 is tends to 0 as h tends to 0, that is already there. Now if I call this is the equation number 7, this is the equation number 7, and if I call this is as equation number 8. Now if we use this value of 7, that is this side and this side, into the equation 6 that we have here, see this, that is the equation number 7 we have calculated. For this value we have calculated equation number 8. So if I use that 2 value here in this equation, one more thing we can get here is that since this epsilon 1 and epsilon 2 are used here, for k equal to 0, it may happen that some other function will come up here. So I just denoted as x3 here. Now using these two values using 7 and 8 in 6, we obtain phi of hk equal to h into, see, phi of hk is this here, fx at this. So fx at this value we have calculated here. So that is fx at x0 y0 plus theta h, fxx at x0 y0. These are the value we are writing, and then plus k into fxy at x0 y0 plus theta h into epsilon 1 theta h into k plus k into theta 2 theta h into k. Then it is minus the value of fx at x0 plus theta h y0. That value we can write as minus of fx at x0 y0 minus theta h fxx at x0 y0 minus theta h epsilon 3 theta h 0. Bracket is over. Now you just observe that this f of x x0 y0 is cancelled out. Theta h at fxx at x0 y0, that is also cancelled out. So the left quantity is nothing but by multiplying this h into inside, we'll have hk fxy at x0 y0 plus theta h square epsilon 1 theta h k plus hk theta epsilon 2 theta h k minus theta h square epsilon 3 theta h into 0. This is the quantity left. Now this quantity I may express as in this manner, that is, you just observe that if I replace this theta k is equal to h in this, so that's why this side we'll have this is theta hk. So this expression I may write as theta h is equal to h square fxy x0 y0 plus theta h square epsilon 1 theta h plus h square epsilon 2 theta h because I'm just replacing k by h minus theta h square epsilon 3 theta h comma 0. If I take h square common and I'm applying the limit as h tends to 0, so this is nothing but the limit h tends to 0, phi of h upon h square will gives you fxy at point x0 y0 plus theta into epsilon 1 theta h into h comma h plus into epsilon theta h comma h minus theta into epsilon 3 theta h comma 0. Obviously this will tends to 0 as h tends to, so here there has to be limit is there, is equal to limit h tends to 0, and you know that this h tends to 0, this epsilon 1, epsilon 2 and also epsilon 3 will be tends to 0. So this will gives you nothing but the f at xy x0 y0. This is because epsilon 1, epsilon 2 and epsilon 3 tends to 0 as h tends to 0. Now in the similar manner as we have discussed here in this argument, That means where we have started with this defining this phi of hk in this manner, and g I have defined as x y of s0 plus a. But instead of that, if we define the another function like this, I am just denoting as capital Gy as f x0 plus hy minus f x0 y. Here we have fixed the y coordinates and we are taking the variable as x. Now we are just fixing x coordinate and making variable as a y. So in that manner, if you can see that, then phi of hk I can write down as phi of hk I may write down as g of y0 plus h minus g of y0. And what is g dash of y? G dash of y is fy at x0 plus h y fy at x0 y0. Now as we have discussed this procedure, that means we have discussed that by defining this g, and then we have expressed this phi in terms of g, and then we have given the argument this fx and fy are differentiable, so g is differentiable. So applying the LMVT, we have this argument, so we'll have this type of equation, and then we'll have similar kind of things we have, and finally we have your phi of hh. It is in terms of this quantity. So if I apply the same argument for capital G and phi, we will have, so following procedure as above, we have phi k upon k square will be fyx at point x0 y0 plus, instead of theta we might have a theta 2 epsilon 4 k into theta 1 k plus epsilon 2 k into theta 2 k. Instead of f2 we'll have 5 epsilon 5 minus theta 2 epsilon 6 0 comma theta 2k, where epsilon 4, epsilon 5 and epsilon 2, they are the function of this, will tends to 0 as k tends to 0. So now I apply the limit k tends to 0, phi of k upon k square will give you fyx at x0 y0. If I call this as equation number double star, and this is as equation star, on this side we'll have limit h tends to 0, phi of h upon h square. So you know that this h is a dummy variable. So therefore, using star and double star, we have fxy at x0 y0 is same as fy at x0 y0. So that is the completes the proof of this result. We'll write a note here that the converse of this result is not true. So that means the converse of Young's theorem is not true. So if you drop the condition that fx and fy are differentiable, then you cannot tell that this condition is satisfied. That we will see via example. So define f from r square to r as f of xy at upon x square plus y square at xy is non-zero and 0 if xy is 0. Then prove that first one fxy at x0 y0 is same as fy at x0 y. Here x0 y0 is nothing but the 0 point, and the second one is fx and fy are not differentiable at 0 0. So this result is actually tells you the things that if you drop this condition fx and fy are not differentiable, then it may happen that the mixed partials are equal. So first one, you note that the same example we have did as a counter example for squash theorem. It is the same example. First part, the proof of the first one is already discussed in my previous video, so I am not going to discuss that here. That is the proving that f of xy at x00 is same as fy at x00. That I have already discussed in my previous video. I may write down the link for this in the description, so you can watch that again if you want. Now here I want to calculate this fx and fy are not differentiable at that point. So I am just proving that fx is not differentiable. I am just giving you as an exercise that fy is not differentiable. So let us calculate what is first fx, because f is given to you, not fx at any point. For that we can just take for any xy non-zero, then it is fx at xy you will have by applying the division rule. What is your function is square y square upon x square plus y square. This is the function. So applying the division rule, you will have x square plus y square whole square, and the denominator is as it is. The derivative of the numerator is 2xy square minus x square y square, as it is derivative of the numerator is denominator is 2x. So if you simplify this quantity, you will have 2x cube y square plus 2xy raised to 4 minus 2 times x cube y square upon x square plus y square whole square. So you just note that this 2x cube y square is cancelled out. So finally you will have x y raised to 4 upon x square plus y square whole square. So finally what is fx at point, any point you will have for non-zero point, it is this xy is non-zero, and at 0 point it will be 0. Now we have to show that this function is not differentiable. So we will show that fx is not differentiable at 0 0. So it is enough to show that. So just recall what is the necessary and sufficient condition for differentiability. It is enough to show that is limit hk tends to 0 0, fx at 0 plus h 0 plus k minus h fx at 0 0 minus k fxy at 0 0 minus fx at 0 0 upon under root of h square plus k square. That does not exist. We have to prove that this does not exist. This is by necessary and sufficient condition for differentiability. Just recall the definition of a differentiable function. And now let us calculate this side. If I call it this quantity as L, so this L equal to, we have limit hk tends to 0 0, fx at hk is there. So by definition of this fx, we'll have 2hk power 4 upon h square plus k square whole square minus h fxx at 0 0, it is 0 because fx at 0 is 0. So fxx at 0 is 0, fxy at 0 is 0 minus k into 0 minus fx at 0 is also 0 upon h square plus k. Then limit hk tends to 0 0, will have it is 2hk power 4 upon h square plus k square raised to 5 by 2, because 2 plus 1 by 2 is there. Now we have to show that this limit is not exist. I am taking a path k is equal to mh because we have to show that this limit is does not exist. So limit h tends to 0. This is L. Instead of k, I have to substitute mh. So that is 2h m power 4 h power 4 upon m square plus m square h square power 5 by 2. So that will gives you limit h tends to 0, 2 times m power 4 upon 1 plus m square raised to 5 by 2, because h power 5 is common out and that cancel in the numerator and the denominator. So that's why it is 2 times m power 4 upon 1 plus m square raised to 5 by 2, which is depends on m. Hence the limit does not exist. As I told you that now you just prove that fy is not differentiable yourself. So with that, let us recall what we have did in this lecture. In this lecture we have discussed the Young's theorem. Young's theorem tells you that if fx and fy are exist in the neighborhood of x0 y0 and if they are differentiable in that neighborhood, then there is a guarantee about the equality of mixed partial. But the converse of that result is not true. We have seen via example that if you drop the condition that fx and fy are differentiable, it may happen that the mixed partial are equal. So with that, I am stopping here. If you like this video, please press the like button. If you have any comment, suggestion or question, please drop down in a comment box below. See you in next video. Till then, bye bye, sayonara.